Hi, students. Today I want to talk about determinants and using Cramer's rule. Um, Determinants are important in all kinds of linear algebras when we have matrices, but they're specifically useful to us in determining whether or not we have solutions to a system of equations, and they can also be used to actually find the solution to the system of equations. In our case, if the determinant is a non-zero number, then that tells us we're going to have one real solution to our system of equations. If the determinant is zero, then we either have no solution or we have a dependent system that has infinite solutions. The determinant of a 2x2 matrix is the easiest determinant to understand, and all larger determinants can be defined using the definition of a 2x2 matrix's determinant. Basically, along the diagonal, we multiply the two diagonal elements together and then subtract from that the product of the other two diagonal elements. So in this case, A times D minus B times C is going to give you a single real number. And that is the determinant, sometimes abbreviated DET, of a 2x2 matrix. Also, notice that these straight lines are actually asking us to take the determinant of this 2x2 matrix. They are very different than the brackets we often use to contain our matrices. Let's do an example with some real numbers here. So if we want to take the determinant of this 2x2 matrix, 5, 1, -7, -2, here notice this is the brackets. So these brackets are just containing this matrix, and we're saying DET of this brackets, meaning take the determinant of this matrix. That is equal to putting the matrix in between these vertical lines. These vertical lines are asking us to take the operation of finding the determinant. So we're going to just follow the pattern from above. We do 5 times -2, and then we subtract from that 1 times -7. And the resulting number is going to be -3. So in this case, this matrix has a determinant of -3. And I'll show you how we could use knowing that our determinant is -3 to help us when we have systems of equations. So for example, if we have this system of equations up here, 5x plus y equals 5, and -7x minus 2y equals -7, we know that we can rewrite that system of equations as a matrix. Now, in our case, notice that our matrix has 2 rows and 3 columns, which means it's not a square matrix. So we can't actually take the determinant of this 2x3 matrix. But what we usually want to look at is just the determinants of the variable coefficients. So we can turn this into a square matrix because we know we're always going to have the same number of variables as we do equations. And so we just use the variables of the or the constant terms of our variables to create a square matrix. And then we calculate the determinant just from that square matrix. And in this case, these are the same as in our previous example. The determinant is -3. So what this tells us is that since the determinant is, -3, a solution does exist. So now, just by taking this simple determinant of the coefficient matrix, we know that we will be able to find a solution to this system of equations. So that's really helpful, especially if you're spending a lot of time solving a system of equations. It's nice to just know if you even have a solution to find. We can do another example over here. -3x plus 2y equals -1, and 9x minus 6y equals 3. We'll convert that into a matrix and then just use the square part, which is the matrix of the coefficients, or a coefficient matrix. when we calculate the determinant of our coefficient matrix, we find that it equals 0. So that tells us that either we have no solution or we have infinite solutions. Okay, and we'll kind of go back and look at our original equations and notice that equation, our second equation, is just a multiple of our first equation, right? If we multiply our first equation by -3, we get our second equation. So in fact, this is a dependent system and there are infinite solutions because these two equations are essentially identical. Now, taking a determinant of a 3x3 is a little more difficult. And there are two ways, there's actually many ways, but two main methods of approaching the determinant of a 3x3. One is using minors, which are smaller matrices within our matrix. And that's kind of the first step or the first method. So when we have a 3x3, we can go along the top row. You're actually allowed to use any row or column to do this, but in our example, we're just going to go along the top row. So we'll take one element from the top row, the first element, A, and then we are going to take, if you eliminate that row and that column, then you're left with a 2x2 square matrix. So our first piece of finding the determinant of a 3x3 is going to be A times the determinant of the remaining 2x2 square matrix when you remove the row and column that contains A. All right, then we're going to subtract from that because you're always going to alternate, add, subtract. B times the determinant of the 2x2 matrix that remains after you remove the row and column that contains B. So that's why we have DGFI that we find the determinant of. Then we're going to add from that C times the determinant of the matrix that remains when we remove the row and column that contains C. Okay, so that's one method for finding the determinant of a 3x3. Basically, as your matrices get bigger, you just break them up in following this pattern until you can get to 2x2 matrices, which we can evaluate for a determinant. Technically, you don't have to go along the top row. You could go along the first column. And then your coefficients here that you multiply by are going to be different, and your minor matrices are going to be different. Okay. Remember to alternate, add, subtract. Okay. Another method that maybe is easier for you to see visually, or maybe not, you get to choose your method, is where we extend our matrix. Notice we take the first two columns and just kind of add them on to the end, and then we are going to multiply diagonally. We're going to multiply all three terms along the diagonal, and we're going to, that product is going to be added, and then we're going to multiply all three terms along the diagonal, that product will be added, and then all three terms along the diagonal, that'll be added. Then coming from the other direction, we multiply all three terms along the diagonal 3 times, and the product of those 3 things is going to get subtracted. So we're going to get 3 things that we add and 3 things that we subtract. And this other method, you'll find, actually ends up giving you the same thing as the previous method, right? So A times E times I is going to be added. If we look up here, we multiply A times E times I. And then A times F times H is going to be subtracted. And if you notice up here, we multiply A times F times H, but when we find the determinant going this direction, or when we find this piece of the 2x2, that's a subtraction. So you end up getting the same terms, and they will add up, or, to the same determinant. Depending on which method you use, you will get the same determinant. So you might want to attempt using both and just see which one you like the best, that you find easiest to keep organized and not make mistakes with. Okay. So that's finding the determinant of a 3x3. Let's take a look at a little example. I've actually got one example for each method. So if we have this 3x3 matrix, we take the first element 2, and we multiply it by the determinant of that remaining 2 by 2 matrix when we cross out its row and column. Okay. We take the next element, -3, and we multiply that by the remaining 2 by 2 matrix when we cross out the row and column that contains -3. Remember, this term gets subtracted. We alternate add, subtract. Now we take the third element of our top row and we multiply that by the determinant of the remaining 2 by 2 matrix. All right. So we do 2 times the determinant of this matrix, which becomes 0 minus -1 times 4. We do minus a -3 becomes a positive times the determinant of this matrix. 2 times 5 is 10 minus -1. So got to be really careful with those double negative signs that often occur here. And then 1 times the determinant of this matrix, which is 8 minus 0, right? Simplify all that stuff, you'll end up getting 49. So that's using the first method that you saw on the last slide, where we take these minors to calculate the determinant of a 3 by 3. Let's take a look at the other method. Let's say we have this matrix -7, -10, 4, 3, -9, 2, 7, 1, 2. We can use our second method by just extending the first 2 rows, kind of tack them on to the end. And then we're going to add the products we get by multiplying these / diagonals, you could call them. And then we're going to subtract the products we get by multiplying these / diagonals. So we add our 3 products and we subtract our 3 products, and that will be the determinant of this matrix. Keep in mind, this and the previous example are different matrices that we're starting out with, so the answers were not supposed to be the same. Now that we know how to take the determinant of a square 2 by 2 and 3 by 3 matrix, let's take a look at Cramer's rule, which actually allows us to use matrices to find the solution to a system of equations. Okay. So if we want to find, so Cramer's rule basically says that the solution to this system of equations in 2 variables is this. So the x value is going to be dx over d, and the y value is going to be dy over d. So what are these big D's and what do they mean? D is the letter we use to represent the determinant of our coefficient matrix. Okay. Now dx is where we've replaced our x column in our coefficient matrix with the constant term column. Okay. dy is where we've replaced our y column in our coefficient matrix with the constant term column. Okay. So all these, the d, dx, dy are going to give us 3 different determinants for these 3 different submatrices of our solution of our system of equations. Okay, and then we can just do dx over d to find the value of the x variable, and dy over d to find the value of our y variable. So let's take an example. We have this system of 2 equations. We'll convert it into a matrix just like this. And then we'll calculate the determinant of the coefficient matrix. We'll calculate the determinant of our sub x matrix, where we're replacing our x column with our constant term column. We'll find the determinant of our sub y matrix, where we're replacing our y column with our constant term column. So when we take the determinant of each of those 2 by 2s, we get these values. So our determinant of our coefficients is -7. So we know we have one single solution. Our determinant, when we replace our coefficient matrix column x with the constant terms, is going to be 7. And when we do the same thing with our column y, we get a -14. So now we can find that our x value, the solution to this system of equations says that x should be 7 divided by -7. So x is -1 and y is -14 divided by -7, which is a +2. And you can go back and check that when x is -1 and y is +2, that will solve this system of equations. Okay, so that's how Cramer's rule works. And some people like this better than our elimination or substitution methods because it's pretty contained. Okay. Now let's check out Cramer's rule for 3 equations and 3 variables. So if we have a system of equations here, now we're going to call the coefficient on x is going to be a, the coefficient on y is b, and the coefficient on on z is going to be called c. And to tell you which equation it goes to, we can label them 1, 2, and 3. Okay. We can still do the same thing. We can use Cramer's rule to tell us that the x value is dx over d, the y value is dy over d, and the z value is dz over d, where the d is the determinant of our coefficient matrix. Dx, again, is the determinant of our coefficient matrix with the x column. The coefficients on our x's are replaced by our constant terms. The dy is our coefficient matrix, but the coefficients on our y's right here in the middle are replaced by our constant terms. And dz is, again, the coefficient matrix with the coefficients on our z's replaced by the constant terms. Okay. To take a determinant for each of these 4 3x3 matrices, but then we can just plug it into this formula to get the solution to this system using Cramer's rule. All right. You always want to do just the coefficient, the determinant of the coefficient matrix first, because again, if that is 0, you're not going to be able to use this Cramer's rule, and you're going to know that your system is either inconsistent or dependent. So let's take a look at an example using Cramer's rule for a 3x3 system. We've got these 3 equations and 3 variables. You rewrite it as matrices, but notice that we kind of set aside our 4th column, which is the constant terms. We're going to take the determinant of just our coefficient matrix, and we get a -12. That tells us that, yes, we do have a solution to this system of equations. We'll find our dx, which is our coefficient matrix with the column for the x coefficients replaced with the constant terms. Same thing for y, same thing for z. You get those 3 determinants, and then we can find the value of each variable just by division. And we've got the value of x, the value of y, and the value of z. So that's how Cramer's rule works, and that is another way to solve systems of equations in 2 and 3 variables. And determinants in general, using the determinant of the coefficient matrix, can tell us whether or not we can find a solution at all, which is sometimes a good first step. All right, that is Appendix E, determinants and Cramer's rule. Take a look over your notes and get started on your homework as soon as possible after watching this video while everything is still fresh. Good luck with everything.